Welcome back. I'm Muggsy, and today I'm going to explain Bohr models. Bohr models are named after the physicist Niels Bohr. And if you saw my atomic theory video, you'll remember that he's the guy who came up with the idea that electrons aren't just kind of suspended around the nucleus like a plum pudding. They actually orbit the nucleus in distinct orbitals. You might also recall that after Bohr, there were physicists like Schrödinger that came up with the idea of quantum physics, and quantum mechanics, and the idea of the electrons orbiting the nucleus in kind of bizarrely shaped electron clouds. Now that's all very well and good, but a Bohr model is still a great way for students and even people like myself, teachers and scientists, to think about how the electrons are arranged in an atom. So let's start by just making a Bohr model. Let's start with carbon. The first thing I would do when constructing a Bohr model of any atom is I would construct the nucleus. Hopefully you remember that the nucleus is made of protons and neutrons. And a carbon atom has an atomic number of 6, therefore it always has 6 protons. So let's kind of stick those in the nucleus. 1, 2, 3, 4, 5, 6. And I've used little plus signs for protons because they have positive charge. You'll also see that the atomic mass of carbon is 12.0110. Of course, you know it's the atomic mass because it's got a bunch of decimal places. It's not a whole number like the atomic number. That means that the most common isotope of carbon has a mass of 12. Now, if it has a mass of 12, that means it has 12 protons and neutrons together in the nucleus. So if it has 12 protons and neutrons, and we know that it also 6 of those are protons, then that leaves 6 neutrons. So let's put 6 neutrons in this nucleus. 1, 2, 3, 4, 5, 6. Okay, so there's our nucleus, 6 protons and 6 neutrons. Now, I kind of get tired of drawing all the individual protons and neutrons every time I make a nucleus for a Bohr model. So what I like to do, and hopefully your teacher allows you to do as well, is instead of drawing them all in individually, I just draw one big circle for the nucleus and then write in the number of protons and neutrons. So let's do that now. Here's my nucleus. I've got 6 protons, and maybe I'll use a different color. 6 neutrons. There you go. Much easier than writing them all out individually. Okay, now how many electrons are there in a carbon atom? Well, the atomic number is 6. The number of electrons is always equal to the number of protons in a neutral atom. That's not true of ions, but of a neutral atom, that's true. So therefore, there's going to be 6 electrons orbiting this nucleus. There's my 6 electrons. I'll put a little negative on each of them, just so you know they're negatively charged. Now, there is kind of a problem with what I just did, and that is, as Niels Bohr taught us, electrons orbit the nucleus in distinct energy levels. But this first energy level can't actually hold 6 electrons. It can only hold 2 electrons. So that means we're going to have to take out a bunch of these electrons. Okay, so now I just have 2 electrons in this first energy level. But actually, even now it looks like I'm making a mistake. And that is these 2 electrons are kind of close to each other. And remember, electrons are negative. So if this electron's negative and this electron's negative, you can think of them as magnets. If you have 2 negative magnets, what happens? They repel each other, right? So if these were to repel each other, they would go to opposite points in the first orbital. So it would actually look a little bit more like this. If I have an electron here, My other electron would be all the way on the other side of the orbit. Okay, now I've only put 2 electrons in, and I know I have a total of 6 electrons, so that means I need to use an additional energy level. Now that first energy level can hold 2, but every energy level after that, at least for representative elements, is going to hold 8. Bohr models are kind of an oversimplification, and they don't really work for transition metals and all kinds of stuff, but for most representative elements, it's a great way to kind of understand the electrons and valence electrons in an atom. So know that as you're working with Bohr models, that it's a way of kind of helping to understand an atom, but it is an oversimplification. Okay, so all other orbitals after the first can hold 8, but I've already put 2 in, right? So if I had 6 electrons and I put 2 in the first energy level, that means I have 4 electrons remaining. And remember, these electrons are negative, so if I have 4 electrons, I want to spread them out equally around this second orbital. And so I might just put them at compass directions, that north, south, east and west. And now I have my completed Bohr diagram of a carbon atom. We have the nucleus, which represents 6 protons and 6 neutrons. And remember, the nucleus is really, really small. If the atom were the size of a baseball field, a baseball stadium even, the nucleus would just be the size of a blueberry. But all of the mass, almost all of the mass of the atom is contained in that nucleus. Because even though it's very small, it's very heavy. Protons and neutrons have a decent amount of mass. Electrons have about, I think it's 1/1000th the mass of a proton or electron. So electrons hardly count for any of the mass of the atom, but they take up the vast majority of the space of the atom, of the volume. Okay, so we have our nucleus with 6 protons and 6 neutrons. Then orbiting the nucleus, we have our electrons. The electrons exist in these very specific energy levels, which are sometimes called orbitals. And orbitals are kind of easy to remember because the electrons are orbiting the nucleus, like the moon orbits the Earth or the Earth orbits the sun. The first orbital can hold 2 electrons, and then all other orbital after that can hold 8. Here's another element that we can draw a Bohr model of. We have potassium. Now, potassium is one of those elements where the atomic symbol doesn't match the name at all because it comes to us from a different language. I forget, in the case of potassium, if it's Latin or Greek or whatever. You don't really need to know. You just need to know potassium is capital K. Okay, so when we're drawing our Bohr model, I always suggest start with the nucleus, start right in the middle of the atom. So let's draw ourselves a nucleus. And in that nucleus, we're going to put our protons. The atomic number is 19, so it has 19 protons. To get the number of neutrons, we take the atomic mass, we round it to the nearest whole number, that's 39. We subtract the atomic number, the number of protons. If there are 39 protons and neutrons, and 19 of those are protons, that means 20 of them are neutrons. So we have 20 neutrons. With some elements, as with carbon, the number of protons and neutrons are the same for a typical atom. With other elements, like potassium, they're different. There's 19 protons, but there's 20 neutrons. This isn't really going to affect things because remember, neutrons don't have a charge. They're neither positive nor negative. They're neutral, and so they don't affect the charge of the atom. So they don't really affect the chemistry of the atom. They do kind of affect the physics, but that's not a big deal. Okay. How many electrons would there be in a standard potassium atom? Well, if there's 19 protons, there are also 19 electrons. And I'm going to just write that here so I can keep track of them. Okay, let's think of our energy levels. The first energy level, as I taught you last time, can contain 2 electrons. I like to space them out evenly because the electrons are negative. They're going to repel each other. That means I have 17 electrons remaining. As you're drawing your Bohr models, I recommend this little trick of just kind of keeping a running tally like I'm doing right here. The second energy level, as I taught you earlier, can hold 8 electrons. So let's take 8 electrons out and put them in that energy level. 1, 2, 3, 4, 5, 6, 7, 8. And again, space them out evenly because they're all repelling each other because they're all negatively charged. Okay, so 17 minus 8 leaves us with 9 electrons. The next energy level, as with basically all other energy levels at this point, can hold 8 electrons. So let's take another 8 electrons out. 1, 2, 3, 4, 5, 6, 7, 8. And that leaves us with 9 minus 8, a single electron. This next energy level, as with all the rest of them, can hold 8, but we only have 1, so I'll just put it wherever. There's my 1 electron. We call this electron, by the way, the electrons in the outermost energy level, we call those valence electrons. That'll become important as you move on in chemistry when it comes to things like ionization and bonding and Lewis diagrams. But for now, we have this beautifully constructed, kind of messily drawn, but whatever, model of a potassium atom. That's the beauty of a Bohr model. It kind of helps you see what this would look like. So if we had a potassium atom, we would have a dense nucleus in the center made of 19 protons, 20 neutrons. Orbiting that dense but massive nucleus would be our electron clouds. The first orbital can hold 2, the next orbital can hold 8 and does hold 8. The next orbital after that can hold 8 and does hold 8. And then the final orbital could also hold 8, but we only have 1 left, so it's only holding 1 outermost electron, which is known as a valence electron. And if you want to practice both reading and drawing Bohr models, head on over to my app, learnsomething.app, which I've built painstakingly over many years. And you can practice both of those skills in a really authentic way. So first of all, with reading Bohr models, we'll show you a bunch of different Bohr models. And based off that information, you tell us what element that is. So here I can see it's 7 protons, 7 neutrons, 7 electrons. So that would be nitrogen. And if you put in something like lowercase n for nitrogen, we don't hold it against you. We give you a little message that helps you fix your answer. And then you can just put in the right answer and continue to progress on that skill. If you get the wrong answer entirely, like this looks like neon, let's say I say hydrogen instead, we'll actually go through step by step and give you kind of the same information that I've given you in this video to help you kind of figure out what element that is exactly for each individual problem in a way that's totally custom to that problem. As well as reading Bohr models, we give you the opportunity to draw Bohr models in a later unit. And once again, we give you the element, in this case lithium. You can kind of look at the periodic table. Lithium, that has an atomic number of 3, so it has 3 protons, 3 electrons, is an atomic mass that rounds up to 7, so therefore it's got 7 minus 3, 4 neutrons. And then you can just go ahead and construct your Bohr model there in a way that's fairly authentic to the experience of drawing a Bohr model down on paper. So create my nucleus with my protons and neutrons, stick my electrons in, 2 in the first orbital, 1 in the second. There we go, successful answer. So yeah, head over to learnsomething.app and you can practice this until your heart's content or until you've really mastered these skills. Once again, thanks for watching.